Hello, and welcome to my first video on calculations for National 5 Chemistry. National 5 is a qualification studied in Scotland and is generally studied by young people about the age of 16. Today we'll be talking about relative atomic mass. Before we start, there's a few things I need to assume you already know. I'm going to assume you already know that the mass number for an atom is the number of protons plus the number of neutrons in its nucleus. It's effectively how much the atom weighs. We ignore the mass of electrons because they are really tiny. You should also know that all atoms of the same element have the same number of protons. So, for example, every atom of chlorine everywhere in the universe has an atomic number of 17. It has 17 protons. If an atom doesn't have 17 protons, it's not chlorine. This is not true, however, for numbers of neutrons. Atoms of the same element can have different numbers of neutrons. That means that they will have different mass numbers. They will weigh different amounts. We say that elements can have more than one isotope. Right, if there's any of that you don't understand or don't know, please seek out my videos on basic atomic structure for National 5 before you proceed with this. Okay, so we're talking about relative atomic mass. Let me first explain why we need it. Okay, let's imagine I have a flask of chlorine. Right, so there's a flask, it's got chlorine in it. I want to know how many chlorine atoms are in the flask. Now I can do that. There are ways of working that out. They're a bit more complicated than I want to go into at the moment, but the basic idea is this. You take the mass of chlorine you've got in the flask and you divide by the mass of a chlorine atom. Okay? If that sounds odd, just think about it this way. Imagine you have a box of chocolates that weighs 100 grams, and you know that each chocolate inside weighs 5 grams. Then the number of chocolates will be the 100 divided by 5 will give you 20. Okay? But we have a problem here. There are two isotopes of chlorine. One has a mass of 35 atomic mass units. The other has a mass of 37 atomic mass units, where an atomic mass unit is the mass of a proton. So which one do I use? If I use chlorine 35, then my answer will come out bigger than it should be. If I use chlorine 37, it'll come out smaller than it should be. What I actually want is the average mass of a chlorine atom. And that's what relative atomic mass is. It's the average mass of an atom of an element. So before we dive into that, a quick reminder about how averages work. Now I'm going to keep this really simple because I find sometimes people panic when they start trying to do sums with atoms and molecules because they can't see them. It sometimes helps to have pictures to express what's going on. So let's imagine you've got a street with 6 houses. Okay? And there's a census going on, so you've got a guy going around taking the census. Yes, I know he looks like a postman, but do try Googling for pictures of census takers, see how far you get. Okay, off he goes to do his job. He goes from house to house to house, counting the number of people in each house. Okay. And then we can add them all up. How many people altogether? Well, you just add those numbers together, you get 15. Okay? So there are 15 people in those 6 houses. Okay? So, what's the average number of people in each house? Well, you'd simply divide 15 by 6. And you get 2.5. Wait a minute though. You can't have 0.5 of a person. Well, not without the police getting involved. But that's the way things are with averages. Averages are often not whole numbers, even if the numbers that go into making them are. That's just one of those things about averages. In the same way, the average number of children in a family is 1.8. But trust me, nobody caters for 0.8 of a child. Okay, so what do we do with this? Right, let's imagine I've got a container of chlorine and it's made up only of chlorine 35 atoms. In other words, every chlorine atom in there has a mass of 35 atomic mass units. 35 times the mass of a proton. Okay, I've also got a container which contains only chlorine-37. So every atom in there is an atom of chlorine-37 weighing 37 atomic mass units. And let's say I've got a device that can measure the average mass of an atom. No, I don't know how that works either, but this is a thought experiment and imagination is a wonderful thing. Okay, now let's imagine that it's all chlorine-35. All the atoms are chlorine-35, there's no chlorine-37 at all. In that case, the average would simply be 35. Okay? Similarly, if all the atoms were chlorine-37, then the average would be 37. If there was equal amounts of each, in other words 50-50, 50% chlorine-35, 50% chlorine-37, then the average would be exactly halfway between them at 36. In reality, the average turns out to be 35.5, and that means there must be more chlorine-35 than chlorine-37 because the average is closer to 35. And in fact, it comes out to about 3 to 1. 3/4 of all chlorine atoms have a mass of 35 and 1/4 have a mass of 37. But let's see how we do this actually doing the sums. Okay, we want to work out the average mass. Now, to work out the average mass of an atom, we need the mass numbers of the isotopes themselves. For chlorine, that's 35 and 37. And we need the relative amounts of each, usually given as a percentage. Okay, let's see how we work this out. Let's assume, and this is the case, 75% of all chlorine atoms have a mass number of 35. 25% of all chlorine atoms have a mass number of 37. Now we're working with percentages, so it makes sense to think about this in terms of 100 atoms, okay? That's simply because we're using percentages, and percentages are numbers out of 100. Okay, out of that 100 atoms, 75 will have a mass of 35 atomic mass units. So 75 atoms out of those 100 will be atoms of chlorine-35. You add up all their masses, that's 75 times 35 is 2,625. So those 75 chlorine atoms added together will have a total mass of 2,625 atomic mass units. Similarly, 25% of the chlorine atoms have a mass of 37, so that you'll have, out of 100, you'll have 25 atoms that weigh 37 atomic mass units. That will give you a total of 925. Now, if we take those totals and add them together, we will get the mass of 100 atoms. 75 atoms plus 25 atoms will have a mass of 2,625 plus 925 is 3,550. Now we take the average. If 100 atoms weigh 3,550, one atom will be 3,550 divided by 100, which is 35.5. Now notice, there is no chlorine atom in the universe that has a mass of 35.5 atomic mass units. Can't have. Because mass number is number of protons and number of neutrons. You can't have half a proton or half a neutron. But again, this is how averages work. An average need not come out as a whole number, even if all the numbers that go into making it are whole numbers themselves. So this then is the relative atomic mass of chlorine, 35.5, the average mass of an atom of chlorine. Okay, to sum up then, that's what relative atomic mass is. It's the average mass of an atom of an element. And this is usually not a whole number. In fact, it's virtually never a whole number. Sometimes it gets pretty close, and sometimes we will round these to get whole numbers, but generally speaking, if we're being precise, relative atomic masses are not whole numbers. To work them out, you multiply the percentage of each isotope, assuming you're working in percentages, by its mass number. Then you add your totals together and divide by 100. And that's it. You probably want to go off and practice a few of those, but that's all for now. Bye.